This video will show how to run external scripts through the command line in ConcreteBending. Let's get started. In addition to using the command line directly, as shown in the previous video, more complex scripts can be generated in any text file and read into the program. This allows models to be easily generated, finite element meshes to be automatically refined, parametric studies to be performed, and much more. Note, when developing external scripts to be ran in ConcreteBending, any valid C# code can be used along with the commands that are already built into the program. The help file contains a number of example scripts to get us started running external scripts. So let's launch the help file and navigate to the external scripts page. We will start out by looking at the two-way slab generator example. This example uses an external script to generate a two-way floor slab with supports. The input section of the script shows that it will generate 3 bays in the X direction, 2 bays in the Y direction, with X and Y bay spacings of 18 and 12 feet respectively. The concrete will be 1 foot thick and a strength of 5 KSI, and the supports will have a size of 1 foot. Next, the script defines the various locations using a couple of for loops. Then the slab is defined. Finally, the supports are added to the model. Let's copy the code to the clipboard, paste it into a text file, and save the file. Now we can type browse into the command line, navigate to the file we created, and open it. Now we see the model that is generated automatically. One advantage of using scripts to generate models is that we can easily change the parameters in the script to create a similar model that, for example, has more bays with a larger bay spacing. Let's change the X bays to 5 and the Y bays to 3 and make the X spacing 20 feet and the Y spacing 16 feet. Instead of specifying a concrete strength, we can use the pick concrete command to launch the material database dialog box, which allows us to pick the desired concrete strength from the database. After adjusting the parameters, we can save the script file and read it back into the program. Now we see the material database open, allowing us to choose, say, 3.5 KSI concrete. After clicking OK, the rest of the script runs and we see the larger model that is generated using the external script. Next, let's look at the refine mesh example script. This script uses a loop to refine the mesh of the ACI 350 tank wall example project until the extreme MX moment converges. The while loop stops once the change in the moment is less than a specified tolerance of 1 kip inch per inch. Note, inside the while loop, the await analysis command is used to pause the script until the analysis completes, so that the largest negative MX moment at the side of the support can be obtained to compare with the moment from the previous iteration. Having already saved the script in a text file, let's load it into the program by entering the path in the command line. Now we see that the mesh of the wall gets successively finer as the script iterates towards the converged solution. Finally, we see that the moment in the wall converges to a negative 48.8 kip inches per inch. The final difference between the moment and its previous iteration delta is less than the tolerance that we set of 1 kip inch per inch, and it took 4 tries before the model converged. Finally, we'll look at the optimized thickness example script. This script builds a simple model that consists of a rectangular boundary supported at 2 ends and loaded in the center with a rectangular live load. The script is used to vary the thickness of the concrete slab to minimize the amount of reinforcement that is needed. This is a nonlinear problem since the larger thickness will increase the load on the structure and add to the minimum steel requirements. A while loop is then used to vary the thickness of the slab in 1-inch increments from the initial value of 12 inches up to a maximum value of 30 inches, and the slab reinforcement weight is calculated for each slab thickness. If the slab reinforcement weight for the current slab thickness is less than the value from the previous slab thicknesses, both the steel weight and the best thickness variables are updated. Note, the await design command is used to pause the script until the design completes, since we have a requirement that the design has to pass both shear and flexure checks to be considered a viable option. Having already saved the script in the text file, let's load it into the program by entering the path in the command line. Now we see the size of the slab progressively increase from 12 inches to 30 inches. After the script completes running, the command line displays that the optimal thickness of the slab is 20 inches with a reinforcing weight of 1.22 kips. In just a few minutes, we've used the command line to run external scripts to generate a 2/8 slab, to refine a mesh to convergence, and to optimize the thickness of a slab. These examples just scratch the surface of what can be done with external scripts in ConcreteBending. We hope you find this new powerful feature useful and it increases your productivity in the program. Thanks for watching and have a great day.